For those of you who haven't met me, my name is Nate Cushman, and I was with Akamai for a few years, and now I'm spending most of my time at a little school down the street from there. And this is joint work with some other people at MIT, Srikant Kandula, Dina Katabi, and John McCloskey. So I'm here to talk to you about transient BGP routing loops. This is opposed to the persistent BGP routing loops that you saw yesterday. And I'm here to convince you both that they matter and that there's something that we can do about them. So what exactly is a transient BGP loop? So let's take an example where we've got a couple of tier 1 ASs and a couple of regional ISPs. Let's call Joe regional ISP and Bob regional ISP. And then we've got an edge network. And let's assume that Bob is a customer of Joe. Just say Joe has some connectivity to somewhere else on the network, and so it's worth it to Bob to have Joe as a provider. And so let's focus on traffic to MIT from AT&T and Joe. And let's assume that we want to do maintenance on the link between Bob and MIT. So as a result of this, Bob's going to send out a BGP withdrawal message to Joe. Joe's going to immediately move to his second best path, which is a path through AT&T. And at almost the same time, a withdrawal message is going to be sent out to AT&T. And at this point, AT&T hasn't yet received the withdrawal message from Joe. And so as a result of this, AT&T is going to route through Joe and create a routing loop. Eventually, Joe will send on his withdrawal message to AT&T. AT&T will move to routing through Sprint, and the routing loop will go away. But in the meantime, we've created a routing loop. So that was an example where we see a routing loop, but does that really happen in practice? So the only previous work that I'm aware of in this area is a Sprint study that was done back in 2002 and 2003. These guys looked at packet traces on the Sprint backbone, and additionally they looked at BGP feeds, IGP feeds, and packet loss on various links on their network. And what they found was that 90% of the packet loss they observed during the study, up to 90%, depending on the trace that they looked at, was caused by routing loops. Additionally, of these routing loops, between 60 and 100% of them could be directly attributable to BGP. So maybe that's true in the Sprint network, but is that true in general on the internet? So we set up 20 different hosts, with all of which had BGP feeds, and for a period of 2 months, we sent pings once every 2 minutes to 70,000 unique prefixes. We also trace routed to each of these prefixes once every 30 minutes. And then we looked at the TTL exceeded responses in order to detect loops. And when we did detect a loop, then we sent additional pings and trace routes to better understand the loop that we saw. And then what we did is we correlated between when we saw a BGP update and when we saw a TTL exceeded message indicating a routing loop. And what we found is that right around the time of a BGP update, there's a significant increase in the amount of routing loops. In fact, almost all the routing loops that we saw were within about 100 to 200 second range of a BGP update. And additionally, even more notably, 10 to 15% of the BGP updates that we saw caused routing loops. This is of all the BGP updates we saw across the 2-month period, across the 70,000 prefixes, across the 20 hosts, 10 to 15% of those updates caused routing loops. However, the problem doesn't stop here. Because not only do routing loops cause problems on the destination, which is seeing loops, they also cause what we call collateral damage, which is additional congestion on the links that are a part of the loop, causing packet loss to other destinations. Give you a quick example of that. Let's say we've got 2 paths, one between ASA and ASD, and another between ASE and ASF. And let's say one of these paths sees a routing loop. And let's say that these 2 paths are sharing a link between ASB and ASC. And that routing loop traverses that shared link. At this point, that routing loop is going to cause additional packet loss on that link. And as a result, it's going to create congestion on the path between ASE and ASF. And we call that collateral damage. So what is the actual effect of collateral damage in practice? So in order to determine this, when we saw a routing loop, we trace routed to that routing loop, and as a result, we could tell which links were a part of that routing loop. And then what we did is we looked at all the other destinations that we were pinging at the same time. And we looked at the packet loss we saw to those destinations that were sharing links on that routing loop. And what we found is that around the time of a link sharing, of sharing a link with a routing loop, there's a marked increase in packet loss. In fact, what we found is for the 100-second window around the time of a link sharing, prefixes sharing a loopy link see about 19% packet loss on average. Now, this is the kind of problem that's very difficult to debug, very difficult for you guys to actually catch in practice, because unless you actually have mechanisms set up to detect this kind of problem, by the time you recognize that the routing loop is causing congestion, the loop will have gone away, and you won't actually realize that the congestion you saw was a result of a routing loop. So, what can we do about this? Clearly, the answer is we prevent forwarding loops. Okay, duh. So, how do we actually prevent forwarding loops? So, let's look a little more closely at what causes these. A loop occurs because one AS pushes a route up to the data plane, but other ASs, not yet aware of that move, try to send packets as if the packets are being routed on the old route. Let's look at that in the example that we saw. So we're doing maintenance on the link between Bob and MIT. As a result of this, Bob sends out a withdrawal message to Joe. And as a result of that withdrawal message, Joe immediately moves to his second best path, which is a path through AT&T. But at this point, AT&T still believes that Joe is routing packets through Bob. And as a result of this, when AT&T receives the withdrawal message, it's going to start routing packets through what is currently, it thinks, is its second best path, which is the path through Joe, causing the routing loop. So let me ask the question, what if AT&T knew about Joe's change? What if we were able to tell AT&T about Joe's change before AT&T made its own change? Before we go into that, however, let me introduce another concept, a concept that we call suspension. And what suspension means is that we continue to route traffic, but we tell the control system not to propagate the route. So what this means is, let's say that I'd like to suspend an interface. So I tell the router I want to suspend this interface. It continues to route traffic. It keeps the forwarding table as is. But it tells BGP to remove the route from all its neighbors. And now this doesn't affect the configuration. This is a one-time change that happens only for a period of time. If the router reboots, it comes back in its normal configuration. We don't have the opportunity to screw things up permanently. And so let's take a look at how we would use this suspension concept in our example. So we want to do maintenance between this link between Bob and MIT, but we're going to know well before we need to do the maintenance. So as opposed to just pulling the link out at the point at which we need to do maintenance, we instead suspend the interface, wait for a period of time for the traffic to go away, and then we pull the link out. So we suspend the interface. Bob sends his withdrawal message to Joe. And now instead of immediately moving away, because the link is still available, Joe is going to send his update message on to AT&T. So in the meantime, AT&T is going to send his withdrawal message to Joe. Sorry, Bob is going to send the withdrawal message to AT&T. And at the same time, Joe is sending his withdrawal message on to AT&T, even though he's still routing through Bob. AT&T will acknowledge that message, indicating that he's processed the update and has already integrated it in at the control level. And as a result, and at that point, then Joe updates his forwarding table and moves to using a path through AT&T. At this point, however, we can be sure that AT&T already knows about the path change. And so when it processes the withdrawal message, it immediately moves to this path through Sprint. And as a result, we've avoided the routing loop. Now, this is just a simple example to try and get the point across. But more generally, because this is the kind of thing that academics do, we've proven that loops are prevented in the general case, and that the convergence properties are very similar to BGP. And if you guys care, you can go look at my webpage to find all sorts of proofs and additional information on this. Lastly, it's worth noting that this is incrementally deployable. That if you deploy this just on your own network, you can avoid iBGP loops on your own network. If you deploy this on your own network and your neighbors deploy it, you can avoid IGP loops on your own network plus any eBGP loops between yourself and your neighbors. And of course, as we deploy it out to the entire internet, we see more and more benefit as we deploy it to more ASs. But here's the part where I ask for feedback from you guys. So I've shown you this example of a planned maintenance event. Okay, so fine. In the case of a planned maintenance event, the link is going to continue to be up. So we're willing to wait. We're willing to delay the move to a backup path because we know that the path that we're currently using is still going to be available for some time. It is worth noting, however, that 20% of BGP updates are caused by planned maintenance events. Additionally, it's almost laughable that we can't bring a link up in the current internet without potentially causing packet loss in the meantime. We can't add redundancy to the network without potentially causing a routing loop as a result of bringing that link up. So clearly this makes sense to run in the case of a link up event where we're willing to wait a little bit longer to start to use that new path that just became available in order to make sure that we avoid routing loops in the meantime. However, what's less clear is in the case of unplanned link down events. When a link goes down and the path is no longer available, we have a trade-off between immediately moving to a backup path and potentially causing collateral damage as a result of that, or staying on the current path and causing packet loss on that path until we can be sure that we won't cause a routing loop. So I'm looking for feedback from you guys on whether or not you're willing to make this trade-off. Are you willing to say that for certain prefixes which are less stable, I'm willing to wait a little bit of extra time to move to a backup path in order to make sure that I don't cause collateral damage to my more stable prefixes? Or are you willing to do this in general in order to ensure that any time you have a stable prefix, it can't be affected by an unstable prefix? So in short, I've shown you that routing loops cause significant performance problems. Even prefixes with no BGP updates can be significantly affected by these routing loops as a result of the collateral damage. And I've shown that a simple change to BGP can avoid all of this. And now I'll take questions. Go ahead.
Thank you very much for this talk. Very interesting. I think that the one question that's hidden in your slides is, what is the time domain during which these transient loops are causing the black holing of traffic? Are we talking about black holing for 10 milliseconds? Are we talking about a problem that actually takes longer because the propagation path is going to take 10 seconds or 20 seconds to make it through the infrastructure?
So what you see is that a single loop may last less than a second, but as the route propagates through the network, many of these loops are created, and so that you can see this kind of to a particular destination, you can see packet loss for as much as 10 seconds as a result of that. Now, that's probably not true in general, but the graph that I showed you shows that the packet loss does last for a significant period around the time of the routing change.
Significant meaning sub-second on average?
Means that it's greater than a second if you include all of the loops that happen between myself and the destination. Meaning if the routing between the destination, around the point of the destination is changing, and that needs to propagate across to me, there'll be many loops that are created between myself and the destination. And the total effect of those loops is often greater than a second, or many seconds.
Okay, just to make sure I understand your point. You're talking about introducing additional state into the routing system in order to capture this transient state prior to going to actually withdrawing the route. And as sort of a side of that, I thought you were going a different path. I thought you were saying the solution is going to be have the withdrawals start at the highest level and then propagate in the reverse direction from the direction that they're currently being propagated.
And that's the effect of what I described, is that it does exactly what you described, is that I send the withdrawal out, it's going to go out to the end, and then the acknowledgements are going to start to come back. And so as the acknowledgement starts to come back, the withdrawal will start to propagate forward across the network, which has exactly the effect that you described. Go ahead.
Hi, Jared Mach, NTT America. So we've seen a number of different issues with these transient routing loops and such, primarily due to router software bugs. And the reason why a lot of these things have been perpetuated for a while is because a lot of people don't They've got the internal update timers of when they actually send different updates and withdrawals and such, and when they actually import them. And we found that it's possible to tune a lot of this stuff with the existing configurations to go and minimize the number of the routing loops and stuff that are seen. And that combined with upgrading to fixed code for different things, which I know is a challenge for a number of providers to go and qualify new code, but it's definitely something people should be looking at.
Okay, I'm interested actually in talking to you about what some of those bugs might be.
I actually have a question for Jared. I was thinking about what he was talking. Patrick Gilmore, Akamai. You say that you think that you can solve these routing loops by tuning your timers. Does that help with your internal sessions or your external sessions?
We found this helps with both, because you need to go and change the timers for what your BGP update intervals are and different things. And it provides the ability to go and control when you send out these updates, make sure that they're relevant and such. And you can always ask vendors for finer grained controls as well on top of that, if that's what you really need to go and control this. Because I think the stability of the internet is really what a lot of us care about these days, because it's now being used, as Sean Donnellan referred to before, it's being used for like 911 and all these life-saving things. And so a routing loop for a little while to Vonage is actually a really big deal.
Now for you. During your talk, you said that you've proven that the convergence time is similar to the current convergence time, that your idea converges almost as fast as today's convergence. What's almost, or what's similar to? What is the convergence delta?
So the basic delta is the time that it takes for those acknowledgments to come back across the network. And since those are sent immediately, it's the time that it takes essentially for a message to propagate across the diameter of the network. So it's convergence time of normal BGP plus that additional delta.
Okay.
Is that another question?
One quick question, Matt Petak from Yahoo here. Your picture basically showed the propagation of information flowing from the point where the suspension happens out to the far edge of the internet, where the furthest upstream point acknowledges and then says, everybody downstream of me, it's okay to go ahead and actually change your forwarding information, your fibs.
Right.
How do you know where the far edge of the internet is? How do you know when the farthest possible upstream has gotten the information and he's got no one else to send it to, so it's okay to start upgrading your fib back down along the path?
So the basic idea is that if I'm not publishing my path to anyone, then I can acknowledge immediately. If I am publishing my path to someone, then I need to wait until they acknowledge to me before I can acknowledge to the downstream. And so as a result, what you do is you send it up until you hit the guys who aren't publishing the path to anyone, until you hit the edge. And then the acknowledgements start coming back through and the withdrawals start propagating.
So your convergence time is now bound by the slowest possible router on the farthest, most distant point of the upstream path.
Yeah, and I mean, in practice, presumably you need to set some timers on this to make sure that you don't, get stuck in a bad case like that. Obviously, in theory, it sounds nice, but in practice, it's going to require some sort of timer in order to ensure that you don't get stuck in exactly that scenario.
So more like I'm going to wait 5 seconds, and if I don't hear back, I'm going to go ahead and update my fib anyway. Okay.
Exactly.
Thanks.
Yep. You want to let it? Okay.
Okay. Hi, Virendra with River Domain. You mentioned about the suspension feature.
Yeah.
Is that you've taken the interface in a passive mode?
What do you mean by passive?
I mean, you're not propagating routes, and you're just accepting routes?
Exactly. You're routing packets normally, but you're not propagating any of those routes out. That's what it means.
All right. Thanks.